Hello friends, welcome to engineering tutorial. So in today's video we are going to resume our discussion on network theory or circuit theory. So we'll be discussing a very basic but most important part of our discussion related to network theory. So I was just going through the videos that I have posted related to previously we discussed network theorems. We're discussing network theorems, reciprocity, Millman, and all that we were discussing in the previously just the last time we discussed about network theory. So I found that videos related to Kirchhoffs laws, Kirchhoff's voltage law and Kirchhoff's current law, that was not there, it was missing. Yes, we have discussed about mesh analysis and nodal analysis. A few questions were discussed, 3 or 4, but as compared to the other concepts where we have discussed 7, 8, 9 questions related to each concept. So KVL and KCL, there were no such questions. So actually I realized my mistake. I should have posted videos related to KVL and KCL and the problems, conceptual problems related to it a bit earlier, actually at the beginning. So because it is very important, basic application of KVL and KCL is very essential in any circuit analysis that you study. After this, whether you discuss anything, DC, AC, whatever, transient analysis, resonance, whatever you see, KVL and KCL application is very important, and a very good understanding of that is essential to even to start analyzing the circuit. It's just like salt and pepper. Okay, it is very essential in the recipe of network theory. Okay, so basic KVL and KCL we'll try to understand, and we'll discuss a lot of questions related to it so that we get acquainted with applying KVL and KCL in different types of circuits. Different types of circuit diagrams will deliberately use different types of circuit structures so that we get comfortable in applying KVL and KCL in any kind of circuit. So Kirchhoff's voltage and current law. Okay, this KVL and KCL. So first let us discuss KVL, Kirchhoff's voltage law. The basic statement of KVL is that the algebraic sum, okay, the algebraic sum of voltages or voltage drops across the circuit elements, be it resistor, inductor, capacitor, whatever it is, drops in any closed circuit, in any closed path loop, that is 0. So what basically it is saying is that suppose we have a circuit, okay, like this, V1, V2, V3, this is, let's say, R1, this is R2. Okay, so let us say the current flowing from V1 is I. Here there are certain things that are important. First, the polarity. This is the positive terminal, this is the negative terminal. Current always flows through a resistor with this kind of polarity, plus to minus, because power is always absorbed. This V1 is supplying power because current is flowing externally from positive to negative. Positive flowing away from positive into the the negative terminal. This I have said many times, but it is very important. Again, the same thing, positive, negative, this is I, plus minus because power is supplied, power is absorbed, and again this here plus minus, like this. So there are two ways of applying KVL. Okay, there are two ways in which you can apply KVL. First is the first sign dominating method. Second is the second sign dominating method. So in the first sign dominating method, what happens is that while writing the KVL equation, for the sign, whether you put plus or minus, that depends on the first sign you encounter while dealing with each circuit element. Suppose you apply KVL in this direction, in this closed path. While coming across each circuit element, be it a voltage source, a current source, a resistor, inductor, capacitor, whatever you come across, the first sign that you come across, the first sign that you put. So one way of applying KVL here is we start from V1. Here the first sign that we came across is minus, here minus. When V1 we came across, the first sign we came across is minus. So that will be minus V1. Then while coming across R1, the polarity, voltage drop, the first sign is plus. So that voltage drop will be plus IR1. Then while coming across V2, the first sign is plus. So that will be plus V2. Then while coming across R2, the first sign we came across is plus. So that will be plus IR2. Then while coming across V3, the first sign that we came across is plus. So that will be plus V3, that is equal to 0. This is one style, the first style of writing KVL, the first sign dominating method, where you put the first sign you encounter while coming across any circuit element. The second method is just the opposite. You write the second sign that you come across, while dealing with each circuit element, the second sign. So here for V1 we apply KVL in the same direction. Coming across V1, the second sign that we come across is the positive terminal, this plus. So here we will write plus V1. Then for R1, the second sign is this negative polarity, minus. So that will be minus IR1. Then for V2, the second sign that we come across is minus. So that will write minus V2. Then for R2, the second sign that we come across is minus. So this voltage drop will be minus IR2. And then for V3, the second sign that we come across is minus. It will be minus V3, that is equal to 0. The summation of the voltages and voltage drops in any closed path is 0. This is the second style of writing KVL equation, the second sign dominating method. Okay, I generally use this style, okay, the second sign, because this is the way I started writing KVL equations from the beginning of my college days. So I am familiar with it, I am comfortable with it, so I always write in this way. But if you write in this way, that is also correct, because either way it is right. Either way it is right, because on both sides we'll get, see, if we bring V1 on the other side of 0, this voltages on one side and voltage drops on the other side, it will be V1 minus V2 is equal to IR1 plus IR2 here, and here also the same thing, V1 minus V2 is equal to, sorry, V1 minus V2 minus V3, okay, V1 minus V2 minus V3 here, I missed that one, V1 minus V2 minus V3, okay, there is another, V3 is IR1 plus IR2, and here also V1 minus V2 minus V3 is equal to IR1 plus IR2. Both ways it is correct, okay, this. So whether you write the first sign dominating KVL equation or the second sign, both ways it will be correct, okay, no problem. Okay, so any way you want to write it, but always make sure that you assign the polarities correct, okay. Then whatever style you adopt, whether it is first sign or second sign dominating method, stick with it, write all the equations in that style, otherwise it will become wrong, okay, you will get confused, you will write one loop equations in one method, other one in some other way, it will get mixed up and the result will be wrong, okay. So always stick to one method, whether it is the first sign dominating method or the second sign dominating method, stick to one, okay. So this is the KVL. Then is KCL. So KCL it deals with currents meeting at particular junction or node. So KCL it states that the algebraic sum of currents meeting at a particular junction or point or node, called as a node which is also called as point or junction in electric circuit, in a circuit that is 0. So according to KCL, let us say we have a point, let's call it O. There are certain currents flowing in and out of it, this, then like this, let's say, then okay. So here let's say this one is I1 flowing into, I2 flowing away, then I3 flowing into, I4 flowing away, then I5, okay, like this. So here what it says, that the algebraic sum of the currents at that particular point O is 0. So here the direction of current is very important. One convention says that the first convention or the first style, it says that current entering the node or point, that is taken as positive, and current exiting, flowing away from the point, that is taken as negative, okay, that is taken as negative. So according to the one convention, current entering is taken as positive and current exiting or flowing away is taken as negative, okay, that is the first convention, this is negative. So as per that, current here entering, the currents that are entering are I1, I5 and I3. So here I1 plus I5 plus I3, and the currents that are exiting, that is I2 and I4, minus I2 minus I4 is equal to 0, okay, this. The second style is just the opposite. the second style says that current entering or flowing into the node is negative and current exiting flowing away from the node, it is positive. So here as per that, current entering minus I1 minus I5 minus I3 plus I2 plus I4, the ones that are exiting, that is positive. This is 0. Either way it is correct. Both the ways it is correct, because if we take I2 and I4 on the other side here, I1 plus I5 plus I3 is equal to I2 plus I4, and here also it is the same. If we take I1, I5 and I3 on the other side, it will be I2 plus I4 is equal to I1 plus I5 plus I3. So whichever style you adopt, you will get the same result, but always make sure that you stick with one style. Okay, normally I use this approach, this one, but either way it doesn't matter, it will ultimately will get the same result. So this is the KVL and KCL, different styles of writing, just two styles, first sign and second sign dominating method. Make sure you stick with one style, get acquainted with it, and whether you are writing KVL or KCL equations, always make sure that you assign the current directions properly, following the rules of circuit theory, assign the polarities correctly, then whichever style you write, it doesn't matter, either way you get the right result. Similarly with KCL, assign the current directions properly, then whichever style you are using, you can use, whether you are comfortable with this one or this one, you will get ultimately the same result. Okay, it doesn't matter. So here we have discussed some basic concepts related to KVL and KCL. Now we'll discuss some questions, some problems related to it, so that we get acquainted with applying KVL and KCL in different types of circuits and different circuit diagrams to get the desired results. Okay. Hello friends, so this is the first question related to KVL and KCL basics, which we'll discuss. So it has been given that in the circuit diagram below, the voltage drop across this 15 ohm resistor is 30 volt with the polarity assigned, which is given, and we have to find the value of R. Okay, this unknown resistance, and we have been given the current values that are flowing and their directions are assigned: 5 ampere, 2 ampere, 3 ampere. Okay, so this is a basic application of KVL. So here we have redrawn the circuit. Okay, so now here we have been given the voltage drop across this resistor, which is 15 ohm, and we have to find the current flowing through it. Okay, simply that. So let's say this current flowing through this resistance 15 ohm is, let's say we call it I. Always current flows from positive to negative polarity because power is absorbed. So here I is equal to voltage drop across the resistor divided by resistance. VR is 30 volt, which is given. Resistance is 15 ohm. So this is 2 ampere. I is equal to 2 ampere. Here 5 ampere is coming. 2 ampere plus 5 ampere, basic KCL application. This current flowing through the 5 ohm resistor will be 2 plus 5, which is equal to 7 ampere. Again, polarity will be like this, plus minus, because current always flows from positive to negative. Okay, here the 7 ampere current comes, then two outgoing currents, 2 ampere and 3 ampere. So obviously the current flowing through this R will be 2 ampere. Again, polarity assigned like this. Now all we have to do is we have got all the currents flowing through these resistors in this closed path, in this closed loop. Now we'll simply apply KVL. We'll simply apply KVL. Okay. So that KVL equation will be, I am using the second sign dominating method. So that KVL will be equation (100) minus 30 volt, which is given already, 30 volt, minus resistor 5 ohm multiplied with 7 ampere current, 5 into 7, then 2 ampere multiplied with this unknown resistance R, minus 2 into R equals to 0. Okay, this is the KVL equation. That implies 100 minus 30 minus 35 minus 2R equals to 0. That implies 2R is equal to 100 minus 65, which is equal to 35. Okay, 100 minus 65 is equal to 35. Yes, that implies R is equal to 35 by 2, which is equal to 17.5 ohms. Okay, so here in this question it was asked to find the value of this unknown resistance, and we found, okay, this. So here the basic thing, it is a combination of both KVL and KCL basics. Okay, first here the voltage drop was given, so the first and the most important thing was to find the current through that resistor. Both voltage drop and resistance are there, current will find out. Then we applied KCL at this node, 5 ampere and this is 2 ampere, so obviously the current flowing through this 5 ohm resistor will be 7. Then we have 2 outgoing currents as this node, so 7 ampere with 2 outgoing currents, total of 5, so remaining 2 ampere will flow through this R. So finally, after getting all the branch currents in this closed path, we applied KVL. Okay, so for this question basic knowledge of KCL and KVL is required. Okay, so we applied KVL, we got the equation and we got the value of R. Okay,